Hello, everybody. Today we're going to talk about free body diagrams. We're going to talk about what they are, how to draw them, what to include, and just the general approach to using them. All right. Uh, First things first, we have to talk about the types of forces. So we may have already talked about this in class, but there are two main types of forces. One we call at a distance forces, and another we call contact forces. Now, of the distance forces, these forces they operate um, at a distance. They do not need physical contact, and these are three forces that you have uh, probably come across before. Certainly, we deal with the force of gravity all the time in our lives. It keeps us on the ground. The electrical force, which you may have come in contact with maybe static electricity when things stick together when you pull them out of a dryer, and of course magnetic force if you've played with um, any magnets that of course will you can feel that force when you're taking a look. Now, the most common of these at a distance forces is, of course, going to be gravity. We will probably not deal with electrical and magnetic in this course. We may talk about them, but we certainly will not be dealing with them. Force of gravity, sometimes you will see it labeled as F sub g. I usually use the variable lowercase w, which stands for weight. So if we're looking at this, the weight and the force of gravity are the same thing. So keep that in mind. You will hear the word weight, you will hear the word force of gravity. Always remember that they mean the same thing. Most of the time, I will use this lowercase w as the variable that represents the force of gravity. These forces over here, contact forces, these require a physical contact. So normal force, that is just the force of a surface. So if you look down here, the block is being pulled by this spring scale, but the block applies a force down to the ground or the tabletop or whatever it's resting on, and the tabletop supplies a force back up, and that force back up is called the normal force. And so you may see this as a lowercase n. Down here they have it as a capital N, or you may see it as capital F sub n. So either one of these is fine. I will use this lowercase n. Tension force, anything with a string or a cable or anything like that, we use capital T. You may see F sub T, but I will use capital T. Applied force is any kind of force that maybe doesn't have a specific label, so that usually is something like this, APP, or maybe it'll have subscript of applied or something like that, but it's just a capital F. It's a general force. If you're not sure what to label a force, you can label it as an applied force. Frictional force, we use these a lot. We will use these a lot. Again, I will be using a lowercase f. I kind of make it a little curvy to kind of separate it from a normal lowercase f. Or you may see capital F with a lowercase. Maybe sometimes you'll see it like that, something like that. But again, lowercase f, that's what I will be using. Air resistance, sometimes this is called drag. Sometimes you will see this labeled as the force of the air. It depends on which source you use or look at, but F sub air is usually how I will show it. Spring force, this is the force that a spring exerts on something. It can be a push force or a pull force depending on the type of spring. All right, so these are the most common forces we will use. You will see these quite a bit. So the first and most important thing when drawing a free body diagram is to isolate the object that you are looking at. So if we were going to draw a free body diagram of this cup, we want to isolate the system. So the system, we want the system to just be the cup. So we'll kind of circle this. I know you can't really see. Let me get a better color here. Let's do red. All right, so we're going to isolate the system. So here's the system. The system is just the cup. We're not worried about anything else touching the cup. It's the cup and the tabletop, I guess you could say. So we isolate that. When drawing a free body diagram, we don't need to draw the actual object. We just draw a dot. And that's it. Real simple. We don't need art projects. We just need a simple representation of the object. And the simplest is a dot. Kind of represents the center of mass of any object that you are observing or analyzing. And so the forces acting on this cup consist of the force of gravity, which we call the weight, and that force of gravity is always pointed straight down towards the center of the earth. And then, of course, the table is pushing back up. And so we have that force, which we call the normal force. And that would be our free body diagram. There are no forces pushing to the side. The object is not accelerating at all. So if you haven't gone through Newton's first law, you can plan to do that soon. But Newton's first law, in a nutshell, says that that the forces acting on an object, if there are any, must be balanced so that there is no acceleration. And so, basic free body diagram, we are only drawing forces. We are not drawing velocity vectors, we're not drawing acceleration vectors, we're not drawing anything else. It is just a simple representation of the object and then the forces acting on it. So now we're going to go through a couple different scenarios of objects and drawing the free body diagrams for them. All right, so here we have some signs. Let me move this out of the way so we can see. All right, so let me do this one on the left. So we have this sign, and we're just going to worry about the two chains that are holding it up. So I'll draw this down here. So we have the force of gravity acting on this sign, goes straight down. All right, so there is the weight. And then we have two chains here. So that means there are two separate forces. So we're going to draw both of those forces. So there is tension 1, and here we have tension 2. All right, so those two forces add up to together. They hold this sign in place, and added up, if we put these vectors on top of each other and added those vectors head to tail, they should equal the weight force. Because if we think about it, this sign is not accelerating, it's not even moving, and so that means that any forces acting on this sign have to be balanced. So they have to add up to 0. So if we say up is the positive direction, then the two tension forces are equal. So we could say T1 plus T2 minus the weight force equals 0. And then, of course, we could rearrange that to say T1 plus T2 equals the weight. And so those forces balance each other out. If we had numbers, we could plug those in. Let me do this sign. So this sign's a little bit different. We have two pull forces. Now this one's a little strange because of the angle. So maybe we'll do this. We'll kind of change this free body diagram because the direction of the angle is a little strange. So we have one force going this way, that's a tension force, and another force going that way, that's the other tension force, so T1 and T2, and then we have the weight going down. Now you might look at this and say, well, how does T1 plus T2 equal the weight? They are two vectors that are at some angle. We don't know what that is. We'll say it's theta. Both of these angles are theta. It's a little strange. Well, here we have to take our understanding of vector components into account. So if we have T1 right here, we know that T1 is made up of a horizontal component and a vertical component. So this would be T1y, and this would be T1x. And then this vector T2, same thing, would be made up of a horizontal component and a vertical component. This would be T2y, and this would be T2x. All right, so a little bit different here, but the same idea. Now look what happens. We have horizontal forces T1x and T2x, and they're pointed in opposite directions, and they are equal. And we also have vertical forces. We have weight going down, and then we have vertical forces T1y, T2y. So T1y plus T2y has to equal the weight, because this sign is also not moving at all. If you need some refresher on vectors, you can go back and take a look at that. All right, let's look at ramps. So if we got any snowboarders in the house, heading down this 13-degree hill, not all that steep, right? And free body diagram for this. Now, I'm going to draw the dot, and I'm going to put a dotted line to show kind of the steepness of the hill. I know that's not exactly the same, but that's okay. We have the weight force still going down. That always goes straight down. Let's say there is friction, because on a real ski slope there is friction. Now there's not a lot of friction, but there is some friction, and that would travel along the hill opposite the direction of motion. So there's our frictional force. And then the normal force, by definition, normal is a mathematics term, which means perpendicular. So if with a snowboarder is on the hill, then the force of the hill pushing back up on the snowboarder is perpendicular to that hill. And that would be our free body diagram. And the object, let's say the object's moving at a constant speed. If the object's moving at a constant speed, then this frictional force is equal to the downhill component of the weight force. So let me draw this a little bit. Let me draw this a little bit bigger. So we have the weight force going down. I'll label that. So, and then the weight force has a perpendicular component to the hill and a parallel component to the hill. This perpendicular component, we call this weight perpendicular, and we call this weight parallel. Well, the skier or the snowboarder is not accelerating perpendicular to the hill, so that means that the normal force has to be equal to this perpendicular component. These two forces have to cancel out. They add up to zero because there is no acceleration. Then the frictional force, if the skier is moving, snowboarder is moving at a constant speed down the hill, then the frictional force equals the weight parallel force. If the snowboarder is speeding up, then the weight parallel force, the downhill force, is bigger than the frictional force. So that is how that works. If it's constant speed, the forces are balanced. If it's undergoing an acceleration, the forces are unbalanced. Pushing at an angle, it's the same idea. This lovely astronaut. We have down at an angle. This would be an applied force. We have the weight force. And then, of course, we have the normal force. Oops. Now notice the normal force is bigger than the weight force, and that is because the applied force has a downward component, and they have to add up to equal 0. How about hitting, throwing, launching? These are all actually just examples of falling, and no matter at what point, after contact is lost, the only force acting is the force of gravity. So anything that is in the air has a free body diagram that looks like.